We're going to talk about an integration technique known as trig substitution here. This is not in our textbook because it is not an AP topic. So this technique is used to solve integrals that might have these various radicals in them. And we will use these trig identities, these relationships that you see here, to kind of motivate and come up with integrals that we could not do otherwise. So first, with those that take the form the square root of a squared minus u squared. I'm going to slide this up a little bit. So we'll talk a bit about how it works and that it does work and how the domains work out the way they should. You don't have to duplicate this part of it. We're just going to have to be able to use it and apply it. So in a square root of a squared minus u squared, if a is positive, then we can say u is equal to a times sine theta. We're going to restrict our domain to be between negative pi over 2 and positive pi over 2. Then that radical that we're going to try to replace with a trig function, the square root of a squared minus u squared becomes square root of a squared minus a squared sine squared. So we've replaced that u by the a sine theta that we're going to replace it with. That's our substitution here. If we factor out the a squared, then we're left with a 1 minus sine squared that we can trade in for a cosine squared. And then we can say the square root of a squared cosine squared is a cosine theta. Now remember, a radical has to be non-negative, but if we look at our domains, then this radical square root of a squared minus u squared is only going to be defined if the a squared minus u squared is greater than or equal to 0. And that means the u has to be between negative a and a. And if we have made our u the a sine theta that we said, and our domain is between negative pi over 2 and pi over 2, then that's going to work. We're going to be where we need to be. Let me slide this over a little bit. Similarly, we can see the other consideration is that square root of a squared minus u squared that we're going to call a cosine theta. For theta between negative pi over 2 and pi over 2, remember that's quadrant 4 and quadrant 1, cosine is positive there, and so we're going to be positioned where we want to, that everything is going to be consistent. So you don't have to duplicate this, but it's nice that somebody thought about this and that it is going to actually work. Now in practice, what we're going to try to do first is to label our triangle in the appropriate way, and then we can replace our integrand, whatever it is we're trying to integrate, with that has x's and dx's in it, by thetas and d thetas. And that will all come from the way we label our triangle. So, and that's the part that I think is the hardest part. Now, it's going to be determined, our clues or cues are going to come from, if we have a square root with a minus sign in it, which one comes first. So it's either going to be a square root of a squared minus u squared or a square root of u squared minus a squared. Whichever one comes first in the subtraction becomes the hypotenuse. So we'll see a little bit later in our third example, the square root of u squared minus a squared, we're going to put u as the hypotenuse. In the one where there is no minus sign, the square root of a squared plus u squared, that becomes the hypotenuse. So that's an important way, I think, to kind of figure out how you're going to go. Now the next thing is we're going to try to decide what is u. Now we will always choose u to be either something to do with a sine or something to do with a tangent, if I can write my u, or something, so either a sine, a tangent, or a secant. Now it is possible to do this using the other trig functions. So in this case, we're going to choose u to be a sine theta, and you could do it with an a cosine theta, but that's not generally done. So to make something that is already quite complicated a little simpler, we're going to just agree to always choose u to either involve a sine, a tangent, or a secant. So in this case, to get our sine theta to be u over the constant a, then we have to label it the way we did, where the legs are going to be u in this position and the radical square root of a squared minus u squared. That just comes from solving using Pythagorean theorem. You could have done these the other way, and that would have led to a substitution that is a cosine theta, which would work, but we're just not going to do that. So once we can figure out how to label our triangle, then because it's going to have this, our integral is going to have a square root of a squared minus u squared in it, we're going to need to figure out what to call that in terms of theta. So we will look at the radical, which we've named as that adjacent side of our angle, and see where the constant is, and we want to pair it with that. So we can see then that a cosine of theta is going to be the square root of a squared minus u squared over a, and then multiplying that a over, that's going to make our radical be a cosine theta. And from there, we would label whatever else we need, including what is that dx going to be. So let's see, I think it makes more sense if we work an actual example. So I'm going to slide this up a bit, and we'll see how this is going to work. So let me bring up my pen here. So we're going to, we see that we have a radical in there, and that's the clue that we may want to do a trig substitution. And if you try to do that some other way, it just doesn't fit. It's not going to be an arc secant because the subtraction in the radical isn't in the correct order, and we don't have a good way of fixing that. So since we can't do it either with a u substitution, because we'd want to make u the inside of the radical, but we don't have the x in the numerator for the du, so it just doesn't work using any other method. So then we're thinking, well, I think because of the radical, it might be a trig substitution. Because it has a minus in the radical, then I'm going to choose whatever is preceding the subtraction to be the a squared, or it could have been a u squared. That is what I'm going to call the hypotenuse. So I'm going to choose the hypotenuse to be 4. Now, another side is going to have to be 3x. So the question is, do I put it on this side or do I put it on this side? And I'm going to choose the wrong side first, just so we can see how to tell that. So if I call this the 3x, then I would say that the trig function that connects this x, the x is what we're really after here, that x with a constant would be a cosine. So I would have cosine theta is equal to 3x over 4. And so I would get then that our x is going to be 4/3 cosine theta. And I don't want to use a cosine. I want to use either a sine, a tangent, or a secant. So then I say, oh, no big deal. I just picked the wrong side to call 3x. So I'm going to change it and call this the side 3x. Then what I'm going to get is that sine of theta is going to be 3x over 4. And then if I multiply by the reciprocal, we'll get 4/3 sine theta is equal to x. That's what I want, is x to be either a sine, a tangent, or a secant. Then I'm going to do Pythagorean theorem and get that this side over here is going to be the square root of 16 minus 9x squared. I'm going to move this down a little bit. So I said that sine theta was equal to 3x over 4. Okay, so now this is good because from the x, I can get dx. So, because I'm going to need that to replace in that integrand. So differentiating this, dx d theta, is going to be 4/3 cosine theta, and then I'm going to multiply that d theta to the other side and say that the dx is going to be replaced by 4/3 cosine theta d theta. So that's going to count for this piece right here. I need to know what the radical is. So I'm going to look at that radical, and I want to pair it up with the constant. So that's going to be a cosine of theta. So we have cosine of theta is going to be the square root of 16 minus 9x to the fourth. Looks like 19. Let me try that. Minus 9x to the fourth over 4. And so that radical that I'm going to have to replace in the integrand is going to be a 4 cosine theta. Okay, I think we've set the stage. So now our goal is to substitute all the x's and dx's for something to do with a theta. So our dx, we said, was 4/3 cosine theta d theta. So I'm going to put that in the numerator. That's where our dx is. That x, we said, was a 4/3 sine theta. That was right here. And our radical is going to be 4 cosine theta. Okay, let's see what we can do with this. Well, it looks like we can cancel one of those cosines. And so we can also cancel the 4/3, and we can pull that 4 in the denominator out. So that's going to be 1/4, and what's left is going to be 1 over sine of theta d theta, which I think we want to think of as 1/4 cosecant of theta d theta. So this is one of our tough integrals, remember. So the integral of sine theta is natural log of sine plus tangent. So cosecant is going to be a negative natural log of the absolute value of cosecant theta plus cotangent theta plus c. Now, we're not finished because now we have to go back from these thetas. They were just all this substitution and replacing these thetas were so that we could get to this point where we can actually integrate something. Now we have to go back to the x's. So we're going to go back to our triangle there to figure out what each of these is. So a cosecant of theta, since sine theta is opposite over hypotenuse, a cosecant is going to be hypotenuse over opposite. So that's going to be 4 over 3x. And a tangent theta is opposite over adjacent, so a cotangent is going to be adjacent over opposite. So it's going to be the square root of 16 minus 9x squared all over 3x plus c. That is our answer. Kind of crazy. So I'm going to go to the next panel, which we'll talk about then our second radical. Let me slide this down. Oh, yep, this is where I want to be. So now we're going to consider the integrals involving the square root of a squared plus u squared. So in this one, we're going to let u be tangent theta, and then we'll see that square root of a squared plus u squared will be a secant theta. That's from our trig identity. And we're going to choose the theta to be between negative pi over 2 and pi over 2. So we can see that, again, how we label this will be the challenging part. And because our integral is going to have an a squared plus u squared in the radical, then we know that's what we're going to call our hypotenuse. Then the question is, which side do we call U and which side do we call A? And remember, our rule of thumb is going to be we want to end up with a substitution for, it says U here, but ultimately we're going to make it X. That X is going to be either a sine, a tangent, or a secant. And if we had put these in the other order, then we would have ended up with a cotangent, which could work, but we're not going to go there. We're just going to always agree to make it a tangent. So that's how we're going to come up with our x, or u in this case, but ultimately it's going to be x. Then we can see that the square root of a squared plus u squared, we want to partner up with the constant, not with the thing that's got an x in it. So we can see that cosine of theta would be the a over the square root of a squared plus u squared, which means that secant theta would be the square root of a squared plus u squared over a, and then we can multiply that constant over, and so we'll get that our radical will be represented by a secant theta. And that will just kind of evolve once we get our triangle labeled correctly. Now, in terms of domains, since we're choosing x to be between negative pi over 2 and positive pi over 2, then we can see that choosing our x to be a tangent theta, remember negative pi over 2 to pi over 2 is quadrant 4 and quadrant 1, and tangent is negative in quadrant 4 and positive in quadrant 1, so it's going to give us the whole spectrum that, x can essentially be any real number. Now we want to be careful that this radical, a radical can only be non-negative. So we want to make sure that what we get, what we're saying is equal to that radical will never be negative. And you can see that from negative pi over 2 to pi over 2 in quadrant 4 and quadrant 1, secant, like cosine, is always positive, and so that meets our needs. That does what it needs to do. So our domains are consistent, and so we don't really have to worry about it. Oops, I bumped something wrong there. So let's see how it works in practice here. Here's our integral. Oh, and I think, and you see there's supposed to be a square root on there. Hold on there. So our integral really has a square root in it. So, and here again, we look at it and we say, well, if it didn't have the radical, we could make it an arctangent, but it does have a radical. And we can't say u is 4 plus 9x squared because our du would need to have an x in it, and we don't have any x in there. So it's not an integral that we can do using any of the techniques we have learned up until now. So we're going to see how we do it with a trig substitution. Now, different than the one we did in the first example, there is no minus sign that you see here. So that when it has a plus, I think that's actually easier, but that may just be me. That means we're going to definitely call the hypotenuse the square root of 4 plus 9x squared. So that's going to make these other two sides. One side is going to be 4, which is our a squared. The other side is going to be 2, because 2 squared is 4. And the other side is going to be 3x, because then when we square it, we'll get that 9x squared. And together, using Pythagorean theorem, they'll add up to be that 4 plus 9x squared. Now, the question is, which one do we call 3x and which one do we call 2? And so let me see if I can make the wrong choice, and we'll see why it's the wrong choice. So suppose I just say, well, I don't know, so I'm going to try 2x and 3. Then what we would say is we want to solve and find out what is x. So we would say that to be x over 3, to get that 2x over 3, that would be adjacent over opposite. That would be a cotangent of theta. And that would allow us to say that 3 halves cotangent theta is equal to x. That would be our substitution. but we're going to agree that our substitutions are going to be x is going to be either a sine, a tangent, or a secant. Because we want a tangent and not a cotangent, then it's the wrong choice, but it's easy to fix. We just switch those. So that means we're going to put the 2x here and the 3 here. I hope this makes sense. So now, what is our x? Well, we can see that tangent of theta is equal to 2x over 3. So 3 halves tangent theta equals x. We always have to solve for x because our integral is going to have a dx in it, and we've got to replace that dx by something that's got thetas in it, and that's what we're going to do here. So we have dx d theta is 3 halves, and the derivative of tangent is secant squared theta. We're going to move the theta to the other side, so our dx is going to be replaced by 3 halves secant squared d theta. Okay, so we've accounted now. We figured out what to do with the dx. Now we have to get an expression for this radical here. So looking at our triangle, we want to get a trig function that pairs our radical with the constant. So the 3 is the adjacent side, so a cosine would be adjacent over the radical. So a secant is going to give us what we want. That's going to be the radical over the constant. And so then it's easy to solve for the radical and say that that square root of 4 plus 9x squared is going to be 3 secant theta. And that's really all our radical, all our integral had was the radical and the dx. So we are going to replace this integral with the dx, which is going to be 3 halves secant squared theta d theta, all over the radical, which is a 3 secant theta. And we can see that we can cancel one of those secants, and we can cancel the 3 there, and so this this integral will simplify a little bit to become 1/2 the integral of secant of theta d theta. So this is an integral we know, if not like. That's going to be the natural log of the absolute value of secant of theta plus tangent of theta. And then we're not finished because now we're going to go back to our triangle and replace these things that have thetas in them with things that have the original x's. So a secant of theta is going to be the hypotenuse over the adjacent. So that's going to be the square root of 4 plus 9x squared all over 3. And the tangent of theta is going to be 2x over 3. And that is the integral of that crazy thing. Let's go on to the next one. So this will be the last one we'll do on this video, and then we'll have a follow-up to this as well. So our third form of a radical involves the square root of u squared minus a squared. That is, the expression that comes before the minus sign is going to have the x in it, and the expression that follows the minus sign has no x in it. It's just a number. Then we're going to choose u to be a tangent theta, but again, this will kind of evolve as we label our triangle. And we'll get that the square root of u squared minus a squared is going to be, and now here's where this has a little complication that we're going to talk about a little bit. It's going to be either a positive tangent theta or a negative tangent theta, and that is going to depend on what our domain is. That is what the interval that we're integrating over contains, and that we'll see in a moment here. So at least initially here, we're going to be between 0 and pi. So if we look at the domains, then for our radical, square root of u squared minus a squared, in order for that to be defined, we need that the inside, the u squared minus a squared, has to be greater than or equal to 0. So that means that u has to either be greater than or equal to a, or that u has to be less than or equal to negative a, so that when you square it, you still get something that when you subtract a squared from it will be positive. So that means for the first part, if we want the u to be greater than or equal to a, that means we're going to have to be in this part of our domain, that we're going to have theta be between 0 and pi over 2. We need to be in quadrant 1. If we want that u, that thing involving x, to be negative, remember here's our u up here, then we're going to need to be in quadrant 2, where tangent is negative. So which one we choose is going to depend on whether, in the case of a definite integral, this will only come up in the case of a definite integral, whether the interval we're integrating over, those limits from a to b of our integral, which region do they come from? And we'll see an example of this in the next video. So what that means then is if our domain, our interval, is going to be between 0 and pi over 2, then we're going to choose the tangent theta to be our radical. But if the interval that we're integrating over involves an interval from pi over 2 to pi, then we're going to choose a negative tangent theta as our substitution for our radical. And we'll do an example of this. But the first one we're going to do here does not have limits, so it's an indefinite integral, and so that's not going to be an issue. We won't concern ourselves with it unless we have a definite integral where we have something up here. Then we're going to have to be cautious. Okay, so we see this integral, and we see that it's got a radical in it, and we try maybe some of the other techniques we know. Can we just do a u substitution? And I think you can convince yourself that's not going to be successful. It doesn't fit any of our forms to be an inverse trig integral, and so we're stuck, except that we can try to do trig substitution. So thinking in terms of now a trig substitution, we see that in the radical we have a subtraction. So that means we're not going to label the hypotenuse as the entire radical. And since the expression preceding the minus sign has an x in it, that's what we're going to, even if it didn't have an x, that expression is going to go as the hypotenuse. So that square root of that 25x squared, 5x, is going to be our hypotenuse. Now, the other two sides here, one side is going to be the square root of 16.4, and the other side is going to be that radical, the square root of 25x squared minus 16. And this is the part that, for me, is always a bit of trial and error. So I'm just going to guess, but I'm going to guess wrong, and we'll see why it's wrong. So if I choose to label the sides this way, then trying to solve for x, we would want to partner it with the side that has just a constant, not the side that's got a whole function in there. And so we would say, well, opposite over hypotenuse would be a sine, and so we would say that cosecant of theta would be 4 over 5x, but that doesn't allow us to easily solve for x, so I don't want to do it that way. I want to do it the other, and it's going to lead to a cosecant. And remember, we want our x's, so I guess let me finish it all the way out. Is that right? So cosecant is going to be that, and cosecant would be, the sine would be 4x, would be 4 over 5x. The cosecant would be 5x over 4. Sorry about that. But that would lead us to saying that x is 4/5 cosecant theta, but we are agreeing that we want to get our x to be either a sine, a tangent, or a secant. So this was not correct, but that's easy to fix. I'm going to switch the two legs. So I'm going to call this side the 4, and I'll call this side that square root of 25x squared minus 16. Okay, now we can solve for x, and we can say that, let's see, we want this to be a secant. So secant of theta is going to be the hypotenuse over the adjacent. And so that means that 4/5 secant theta is going to be our x. And remember, we want this because we need an expression for dx involving theta. And so our dx is going to be 4/5, and the derivative of secant theta is secant theta tangent theta, and we'll tack the d theta on there. Now we need an expression for x. But we already have that here. And we need an expression for this whole square root. So we're going to partner our radical with our constant. And so that's going to mean we have a tangent of theta is the square root of 25x squared minus 16 over 4. That means that 4 tangent theta is what we're going to use to substitute for that square root of 25x squared minus 16. Okay, so here we go. The radical up on top is going to become a 4 tangent theta. The x in the denominator is going to be our 4/5 secant theta, and our dx will be replaced by a 4/5 secant theta tangent theta, d theta. Okay, I think we've accounted for everything there. Let's see if anything simplifies. I think we can cancel this secant theta with that secant theta. We can cancel that entire 4/5 with that entire 4/5. And then our integral becomes the 4 we can pull out of that, and we'll get a tangent squared theta d theta. So we've been doing all of these trig integrals lately, which is going to come in handy. Hopefully we recognize that we're going to replace the tangent squared theta with the secant squared theta minus 1 d theta. So that integral is going to be 4. The integral of secant squared is tangent theta. And then we'll get a minus 4. And the integral of 1 with respect to theta is going to be theta. This is interesting. We've not seen this before. Let's see. Now we're going back to our triangle. So the tangent of theta is opposite over adjacent. So that's going to be that square root of 25x squared minus 16 all over 4. It's kind of convenient. We'll get to cancel that. And then minus 4 times theta. Now, theta, we're going to come back to here and say that theta is going to be the arc secant of 5x over 4. See it? Now we're solving for theta there. So that's going to be an arc secant of 5x over 4, and then a plus c. Crazy, crazy, crazy. Okay, very good.